All right. Good morning, everybody. All one of you. And my guess is that it's Connor. If I had to guess, I'm going to put money down that Connor's watching. So, whoever's there, prove me wrong by saying hi. And Connor, if you're there, prove me right by saying something in the chat. So, excuse me. I am definitely not myself this morning. I did not sleep well for whatever reason. I just can't seem to get into a decent routine, and this is starting to drag me down a little bit. This is getting old. Oh boy, is it getting old? I would love to get back to some sort of normalcy, but it doesn't seem like it's going to be happening anytime soon. Hey, Connor, I was right. Now there are currently 3 people in this chat thing. I'm one of them up here on my left. Connor's the other person who I thought for sure we had. So now we're up to 4. Kaylin, you're my second person. I always can count on you too. And then there's another person in here too. But there's only 2 likes, so this seems to be a little mismatched. Wow. Is it jumping? Is the image a little buffering a little bit? Says I have an excellent connection. I'm not sure what's going on there. Whatever. Okay. Anyway, let's get started. So today I'll be doing 8 a.m. for non-honors and 9 a.m. for honors. Both of you guys will be getting assignments posted on your individual Google Classrooms later today once I get that figured out. I just got to put the assignment together. The assignments will be due Thursday and probably have another assignment posted on Friday. So today is new stuff with an assignment. Tomorrow will be like a breather day. At least that's what they've been calling it. And then Thursday, new stuff, talk about the assignment. And then Friday be new stuff, probably have a new assignment. So it's something like that. I'm trying to work it out where I can have 2 assignments every week to get you guys some grades and have some sort of consistency and pick days where the assignments will always be happening. So I think Tuesday's a good day for the assignment just because that gives me Monday and Tuesday to go over new stuff, and you get the idea. It's trying to manage the flow of the class and get it to work from there. So keep an eye out on the Google Classroom shortly for the assignment today. Now today, let's talk about a thing called percent error. Now the percent error, it's simply a formula that you're going to be learning, and it's not all that difficult. Let's see if I can aim my camera a little bit here. There you go. Okay, so percent error, you're going to have a formula. Now the whole point of percent error is to find how accurate a measurement is compared to the, you ready? I'm going to give you an abbreviation, actual value. So AV is actual value, okay? So this is what the whole point of today's lesson is going to be. Yesterday we learned some vocab. Piece of cake, you have those definitions, go back, watch those videos. Today you're actually going to learn some math, okay? And then Thursday, more vocab with some new math on top of that. So the idea of percent error is to find out how accurate a measurement is compared to what it should have been, okay? So let's give you the formula, and then we'll talk about how this would be used in certain word problems and what have you. So here we go. All right, the formula for any percentage you ever calculate, no matter what you're dealing with, will always be the percentage that you're trying to find is equal to the part divided by the whole, and the last piece is times 100%. All right, so if you look at this, you're going to probably have some units in here as well, which we'll get into eventually. But the units should cancel out from the denominator and the numerator in this portion of the formula. The final part is going to have a unit of percentage because this is the only unit left over. Okay? I hope that kind of makes sense. It's always part divided by whole. It's going to be up to you based on the word problem you see to identify those pieces. Now, to rearrange this and apply it to the scenario of a percent error, you're going to have, instead of part divided by whole, it's always going to be, I know you guys taken some math classes before, so you may have seen something like this. It's called the absolute value of your error divided by the actual value. Okay? So it's the absolute value of your error or your mistake, okay, divided by the actual value. Now, your error is going to be, right, there's a whole nother like thing there. The difference between the actual value minus the experimental value. So your error is your mistake. It's the difference between what you should have got and what you did get. Okay? So you figure this out. This will be in the question, these two things. You might even have this given to you right away. If this is given to you right away, just plug it in the formula divided by this thing. But no matter what, your actual value will always be given to you in the question. Without that, you can't do this formula. Okay? So then we're going to make a rule here that you need 3 places after the decimal for your answer. All right? So 3 places after decimal. Just so we have some consistency. So we should all be getting about the same answer. Okay? So I'm going to erase some of this stuff, and we're going to look at 2 scenarios, 2 cases where we can kind of compare the percent error of 2 different experiments, so to speak. So let's erase this part here. I'm going to leave the formula up there so we can look at it. All right, let's scoot this up a little bit so I got more room. There you go. All right, so let's look at case number 1 versus case number 2. Okay? Now, this is worded very carefully, okay? I got to be very, very specific when I say this. You ready? There is a difference between how far off you were and how wrong you were. So let's clarify that before I move forward. This makes more sense, all right? You ready? Here we go. There's a difference between how far off and how wrong. Okay? This is your error. This is your percent error. So don't get these 2 terms mixed up. Okay? How far off from the actual value is very different than how wrong you were. Now let's put that into perspective with your grade. Okay? So for instance, let's go back to this thing. I'm trying to think of the scenario that I would have said in class. So, let's say you're taking a test in class and it's based on 100 points. Well, you get 10 points wrong, right? 10 points off of what you should have got. That means you get 90% correct, right? Well, 10 points off is also the same thing as saying 10% wrong. 90% correct, 10% wrong. You see where I'm going here? It's got to add up to 100. But that's out of 100 points total. Now, let's say the quiz or the test or whatever it is based out of 178 points. Whatever, right? Just some random number, 178 points. And you get 10 points off. Your error is the same because it's the error, your mistake is 10 points. So you're 10 points off. But it is no longer 10% off. Does that make sense? So it's all based on the actual value. Your error is different than your percent error. Don't get them mixed up. Your word problems that you're going to see are going to have both of those terms in there, and a lot of people end up getting them switched and solve for the wrong thing, and they get confused, and it doesn't work out. So I'll say it one last time. Your error, how far off you were is very different than how wrong you were, your percent error. Okay, I hope I drove that home pretty good. Let's go back to this screen here and take a look at scenario number 1 versus 2. All right, so scenario 1 is you're 10 centimeters off when measuring what was it? No, that's not what I want to do. Without the PowerPoint in front of me, it gets a little tricky, memory. But I'm going to say 9 centimeters off of 10 centimeters versus scenario number 2 when we are 9 centimeters off of 100 centimeters. So let's clarify what all these are. This is basically a summary of 2 different experiments that could have happened, okay? Let's get this guy and put him down here. All right. So this is a summary of 2 different experiments. In experiment number 1, you were supposed to have gotten 10 centimeters. You're just measuring the length of something. So you get 10 centimeters. All right. You know it's 10 centimeters, but when you go to measure it yourself, you screw up somehow, and you're 9 off, which means you either measured 1 or 19. Make sense? Okay? So you either measured 1 or 19. Either way, you're 9 off. It doesn't matter what the final thing was, 1 or 19. What really matters is how far off, or your error, your mistake in measuring 10. You had a mistake of 9 centimeters. Okay? If you do the math, that's your error. That's 9, your error, divided by the actual value of 10 times 100. You're going to get 90% error. So you're 90% wrong here. You were 9 off, but you were 90% wrong. Okay? Let that try and sink in there for a moment. Now, if you look at this other one, we are 9 off, same error. So which means in this particular case, it was supposed to be 100. You really measured 91 or 109. That doesn't matter. What really matters is how far off you were again. 9 centimeters, that's your error, divided by 100, your actual value, times 100. This comes out to be 9% error. So in this one, you were 90% wrong. In this one, you were only 9% wrong, but you had the same exact error. So hopefully that can prove to you that being, or how far off you were, is very different than how wrong you were. Give me some feedback, guys. Let me know that's making sense. And I'm going to get an example question prepared while I wait for the lag to show up. So I have the PowerPoint on my other computer over here, and we're going to get a example question that I would have shown you in class. I just got to bring it up on my screen. And let's take a look here. Actually, no, I don't have one. Okay. Let's make one up. How's that sound? In the meantime, I'm waiting for you guys to give me some sort of feedback if you're following along or whatever, okay? Now, these questions that you're going to see in today's assignment are going to be primarily percent error, because this is a calculation that everybody should know how to do, and it will be used later on in the course for more complicated questions. It's just the nature of this kind of class. You build, you learn a concept, and you go from there. So let's make up a question, okay? And I'm going to give you a moment, and you try to figure it out. You can always pause the video and then come back and catch up. So let's say you're measuring. Let's do mass. Mass is a good one, okay? So mass is going to be measured in grams. We haven't really talked about that specifically just yet, but that will be involved in this chapter that we're doing and starting this week. So anyway, let's say I give you an object, and you know for a fact it's, and I'm making this up, so we'll have to do the math together. A mass, okay. I'm trying to word it like a test question to give you some practice on that. So an object has a mass of 65.3 grams. That's your actual value. It just tells you right out. An object has this mass. So context clues of the question is you have to read the question and figure out exactly what the actual value is. There's going to be more than one number in here. And Connor, I'll address that question you have about the absolute value in this particular question. Okay? An object has a mass of 65.3 grams. A scale reported the mass of reported a mass of let's just say 73.9 grams. All right, and then the question: what is the scale's percent error? Okay? So that's a question. It could be very, very similar to something that you might see on today's assignment, or it might even be similar to what you would see on like the test that you would get in class. So here's the deal. And Connor, I'm going to address that now with the percent, with the absolute value. In the end, it doesn't matter if you take this number. In this particular case, this is the experimental value, and you subtract 65.3 from there, the actual value. And you would get a positive number, right? Because this one's bigger. Or you could take this and subtract that, and you would get a negative number. If you take the absolute value, you're always going to end up with positive. So the absolute value is there to ensure that you always get a positive percent error. Okay? So first thing you got to do is find your error. That's step one. Okay? That's going to equal 73.9 minus 65.3. Or 65.3 minus 73.9. It doesn't really matter. I got to sneeze. Jeez. That one snuck up on me. Okay. So if I were to do this math, I'm going to get 8.6 grams. Now, if I did it the other way around, I would get negative 8.6. Well, then the second step is to use the formula to solve for the percent error. And you're going to use the absolute value of this thing. So whether you got negative or positive in this case, it doesn't matter because it's going to end up being positive. So you just do 8.6. And the actual value, you got to kind of read between the lines here and figure it out, 65.3. And then you multiply that by 100, and you get your answer, which in this particular case is going to be less than 10%. So, Connor, let me know if that makes sense. And in the meantime, I'm going to bring up the calculator on another screen and actually do the math. 8.6 divided by 65.3 times 100. 3 decimal places. It's more than 10%. I screwed up. So 3 decimal places, 13.170%. All right? That's what you should have got if you're kind of hanging around. Okay, Connor, let me know again if that addressed your issue with the absolute value. It's the same formula. It's just I was explaining how to figure out your error. Okay? All right. Let's erase this, and we'll do another one. Kind of do a similar one here. Now that question's gone. I don't remember what it was. I'm going to lose it forever now. So if you have any specific question about that, you're going to have to give me some info. All right, let's look at another one. Let's say we're doing something with density. Now, density has a unit of grams per milliliter in general, right? That's most of the time. So let's say you had a block of aluminum, okay? And I'm going to say when you see something like that, right away, that's a clue that most of the time the next number you see is going to be the experimental value. So watch. You calculate the density of a block of aluminum to be 2.95 grams per milliliter. Okay? Cool. So that is your experimental value. So that's what you figure out. All right? Now moving forward. However, the actual value, so AV, actual value, is 2.70 grams per milliliter. All right? Question would be, what is your percent error? All right, hopefully you guys are with me. That's not too bad. I'm trying to word it in a way that makes the most sense given our circumstances here with not being in class. So I'm trying to be very careful. Anyway, same idea. You could pause this and give it a shot. I'm going to, in a moment, move forward with calculating the answer, and you can kind of compare your answer to what I get. So you would just use that same formula. The percent error is going to be equal to my error, which is the actual minus the experimental. In this particular case, I was off by 0.25. So I'm going to take the absolute value of 0.25 and divide it by the actual of 2.70. Now, I'm not writing in the units. We haven't really talked about the units yet, but notice that mathematically they would have canceled out anyway, like I mentioned a while back. Last step would be multiply it by 100. And then I'm going to do the math over here. So 0.25 divided by 2.70. Forgot that. Times 100. 3 places after the decimal. You should get 9.259%. That should be your final answer. And I think you guys are quite capable of doing that. All right? Let me move it up a little bit so you can see it. So 9.259% should be what you get in a question like that. To be honest with you, that's the basis for percent error. There's not much more that we can do with this topic, given the circumstances. So, in a moment, I'm going to give you guys a chance to get caught up, and if you have any questions about this question specifically, now's the time to ask. I'm going to give you a chance to do that, and in the meantime, I'm going to stall, just because of the silly delay we got to deal with. So, the assignment that I'm going to put up will probably have, 5 to 10 questions regarding everything we've covered so far, whether it's the vocab, which probably won't be too much, but you're probably going to have a bunch of percent error questions. Okay? So that's going to be the basis and the overwhelming topic of this assignment you're going to get later today. I just need to do my 9 a.m. live stream and then put the assignments together. So that's that. Okay? So far, I don't see any questions. And, I'm checking the status of the actual stream up here. This whiteboard seems to be making a big difference. Excuse me. I think it's easier to see. It's way more of a contrast, and I think it works. So what do you guys think of the whiteboard if it's a good addition to this setup? In the meantime, I have some other ideas where I'm thinking about making a purchase, a piece of equipment that would allow me to have, I could switch cameras on the fly, kind of like what I'm doing now, but to switch cameras, I got to pick up the mouse, go to the software, blah, 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 find it, and I make it real small so I can see the whole screen, and it's very cumbersome. If I have this piece of equipment, I can just hit a button, and it's an actual peripheral device that you plug in USB and it controls everything. It's a macro keyboard. Look up Elgato Stream Deck if you're curious. But that's what I'm thinking about buying next. And then putting a whiteboard up on the wall over here, and I can have multiple cameras because I'm a dork, and this is what I like. All right, so that's that. Seems to be no questions. I'm going to call this live stream done. I'm going to go back to the pause screen in a moment, and yeah, keep an eye out for that assignment on Google Classroom. Today's Tuesday. We'll make that due Thursday. Cool? All right. I'll talk to you guys again tomorrow. All right? Yeah, that's that. All right. See you then. Bye. All right, boys and girls, here we are. We're going to get rolling. This is the 9 a.m. portion of today's live stream, and this is specifically for honors. So we're going to be covering, excuse me, more information about that empirical formula and, figuring out the empirical formula for the percentage and then taking the empirical formula to the molecular formula. So as of right now, there's one person watching, and guess who it is? I'm watching it on my other computer right here. So there's no one watching this. Two people. All right, so somebody logged in. Okay, it's 9 o'clock. People are just still asleep, I guess. All right, so what I'm going to do is I'm going to come over here to this computer that I have set up, and I'm going to pull up the PowerPoint. And in doing so, will give me example questions. Okay, so I'm just going to go to the next example question, and I'll be able to look at it over my shoulder and, write down all the specific information that I need on the whiteboard, okay? So the example question that we're going to do is just the next step. So we'll do this example to kind of get you rolling, and I'm going to show you every so often you're going to come across a situation where it's just one more step. What's up, Zach? I just saw you log in there. All right, so this is the PowerPoint that you would have seen in class. I know you can't really see it all that well because there's a glare or whatever. I'm trying to work it out. Oh, hey, good morning. I'm trying to work it out where I can show you the PowerPoint on the screen. I'm working some things out. I got some plans in the future to make this live stream a bit more professional, and I want to be, how they do those silly things in the yearbook. Most likely to succeed, teacher with the best dressed teacher and crap like that. Well, I'm definitely not the best dressed teacher, but I might be the one with the most technologically advanced live stream. That's the one I'm going for. All right, so here's a question. I'll read it to you, and then I'll write down specific stuff on the whiteboard here. All right? So it says a compound has a mass percent of 68.848% carbon, 4.952% hydrogen, and 26.203% oxygen. So it's got carbon, hydrogen, and oxygen. It also has a molecular mass of 122.12 grams. So that's the molar mass, okay? Another way of saying molar mass. What is the molecular formula? Okay, so let's go to the whiteboard. And if you remember, earlier we learned how to go from the formula to the percentage, right? Well, now, yesterday we were talking about starting the question with the percentage instead, and we figured out the empirical formula, which then gives us information to finally figure out the molecular formula. All right, so this was a couple days ago. This was yesterday. All right, so we'll do this question as kind of a warm-up or whatever, and just a further extension. So you cannot get the molecular formula until after you figure out the empirical. And this question's asking for the molecular, so we got some work to do. All right, so I'm going to write down all the necessary information that we need. We know we have some carbon, hydrogen, and oxygen. We're going to have to do some work for each and figure out what's going on. Now, remember yesterday I said if you have your percentages in the question, just switch them to grams. The idea is that you're assuming you have a 100-gram sample, and with the percentage, that means you have that many grams. So we have, in this case, 68.848 grams of carbon, and for hydrogen, we have 4.952 grams. And oxygen, we got 26.203 grams. Now, this should add up to 100% or 100 grams. It might be off by like a thousandth, very, very small, tiny amount, but it should be about 100 grams. Otherwise, something's wrong. Anyway, let's convert each of these to moles. That's our first step. And to do that, you need the mass of each directly from the periodic table. Some of these I have memorized. Like carbon is 12.011. Hydrogen is 1.00794. Oxygen is 15.999. So I know it's kind of difficult to see. Some of my handwriting's not the greatest. But if you're following along, all you need to do is get yourself the periodic table, whether it's in another tab in your browser or you have a physical one at your desk there, wherever. Just get the masses from the periodic table, and then you're converting them to moles. We've already known how to do that. All right, next. You cannot round in this section because otherwise your ratios will be all messed up. So I'm going to go to another tab here, and I'm going to start doing this math. You guys can start doing that as well. All right, this first one is going to be, I got 5 sig figs here, so 5.732, one more would be 1. This next one, divided by 1.00794, with 4 sig figs, I got 4.913. You guys should be getting about that. It might be off in decimal place here and there. Some periodic tables are slightly different, meaning that they have rounded their mass to a different level than other periodic tables. And because of that, you might get a different mass and a different final answer. With sig figs, this one comes out to be... All right, so next. Here we go. So those are my 3 ratios. Now, you could argue that the formula is C 5.7321, H 4.9130, O 1.6378, but that doesn't make any sense. The final step would be to divide each of these by the smallest amount, which is, in this case, the one for oxygen. So this is going to be 1. Let's write all this down so we have consistency, and then I'll figure out the math. I'm kind of running out of room here. I got to adjust my camera angle, I guess. That'll be another day. 7321 divided by 1.6378. And if you guys see me make a mistake, you're going to have to let me know. All right, now this one for carbon, it's got 5 sig figs here, and I got 5 sig figs here. So my answer's got to continue being 5 sig figs, all right? So I got 3.4, that's 2. 999. 3.4999. Hopefully you guys got something real similar. Let's take care of hydrogen. I need 4 sig figs here. So that comes out to be 3.000. Let's check if that's all on camera here. Okay, let's scoot this over just so you can see my answers. All right. Now, this should be your ratio. So I got C 3.49. Wait, that doesn't make any sense. Right? Now, remember I told you that there's going to be some situations that require one extra step. Now, if this was just a whole number like these others are, these other 2 are definitely whole numbers, 3 and 1. You can move on with your life. The problem is this is not a whole number. This is 3.5. Right? You can't round that to 3. You can't round it to 4. It's way too far away, okay? So there are circumstances where the final step is you have to multiply this by a whole number to get this portion to a whole number. But if you do that, now you're messing up your ratio. So whatever you do here, you're going to multiply the others as well. So let's say I multiply this by 2. Doesn't that make that now 7? So C7, H6, O2, multiplied by 2, by 2, by 2. So I got 7, 6, and 2. So this now must be analyzed to make sure it's a proper empirical formula. So for instance, you got to make sure it can be reduced. If this can't be reduced, it's already the lowest whole number ratio and therefore your empirical formula. So you're now going to kind of label that as your empirical formula before you move on to the rest of the question. Now, before I do that, I want to make a mental note here to say that we're going to come back to this portion after we finish this question. That multiplied by 2 only happens every so often. It's not every question. If you come up with a situation where it's something like this, a decimal in this portion, then you're going to multiply it. And I'll explain further in a moment. So what I'm going to do now is I have my empirical formula. I'm going to erase everything, okay? And what I'm going to do then is show how to take this empirical formula to the molecular. All right, so the empirical formula that we have, we said is C7H6O2. All right. Also in the question, it said we had a molar mass of 122.12 grams per mole. All right, the last step to get to the molecular formula is to take that molar mass and divide it by the empirical mass. And then that'll give you a whole number. Okay? And this whole number will tell you how many times to unreduce that. So let's just eyeball this. So 7 times 12 is 84. Plus 6 is 90. Right? Another 32 for your oxygens. 90 plus 32 is 122. See where I got that? So 122 divided by 122 comes out to be 1, which means you unreduce this one time. In other words, the C7H6O2 is not only the empirical formula, but it's also the molecular formula. Sometimes that happens. Sometimes where the molecular formula is already the most reduced form, and it turns out to be the empirical. I fully expect some of you guys to have to go back and watch that again. Don't feel bad if you have to. This is a slightly tricky idea where you're solving a problem with prescribed steps. No matter what the word problem is, you go through the same steps. You find the empirical, and then you divide the molecular mass by the empirical mass. But every so often in finding the empirical, you might have to multiply it by something. So here's the deal. If we go back to the, hey, Matt, what's up? If we go back to this thing here, right? Now, we got something 0.5, right? Something 0.5. Now, we said if we multiply that by 2, we should get a whole number. You got to make sure you multiply all of them by the same thing. Otherwise, you're now going to ruin your ratios, okay? There are other possibilities, though. This is not the only time where you got to multiply. Every so often, you're going to get a couple of different possibilities. Oop, skipped one. All right, so if you get something 0.25, you have to multiply that by 4. But then multiply everything by 4 in order for it to make sense. If you get 0.33, it's going to be 3. 0.66 will be 3, and 0.75 will be 4. So you see the pattern, 4, 3, 2, 3, 4. Okay? It's not terrible. Now, I know this is the first time you've seen this, so you might be like, whoa, what's he talking about? It just takes practice, doing more and more questions, and it gets you better skilled at these word problems. So let's do another one. Here's a good question. All right. Very good question. Okay. I'll read it to you, and then I'll explain, all the information that you need along with that, and I'll write it on the whiteboard. So I got 750-liter container. Sounds like gas. It says a container of gas at STP. Perfect. Has a percent composition of 27.29% carbon and 72.71% oxygen. So you only got 2 things. I'm going to write this stuff down so far, and we'll finish reading the question. So I got a 750-liter container. Oh, let's go back here. This is what I want. Okay, so 750-liter container. That's how much gas you have. Now, you don't know what gas you got yet. We're going to have to figure that out. We know that the gas is carbon and oxygen. So for carbon, it's 27.29%. And for oxygen, it is the rest, 72.71%. All right? It says you're told that the empirical formula is also the molecular. Okay, very good. So if we can figure out the empirical formula, that tells us the molecular formula, and in turn tells us what the gas is that we're dealing with. We don't have to do any other figuring to determine what the gas is. Here's the question. How many grams of oxygen are there? All right, so let's go to the whiteboard, and we'll transition to that. How many grams of just oxygen? Okay? That's what we're trying to figure out. Let's put the question mark at the end of the question, shall we? All right? That's what we're trying to figure out. Here's the information that we have. This is what the question's asking. Okay? We know we have 750 liters of a gas, but we don't know what gas we have yet. Let's start by figuring out what the gas is. Now, at first glance, my experience looking at this just tells me, well, it's either carbon monoxide or carbon dioxide. Just chances are, right? Those are two simple compounds, very, very common. We know that they're both gases. Let's see what we got. We're kind of going on that expectation, but let's not be shocked if we're surprised. So let's figure out the gas. I'm going to move this up here a little bit. We'll come back to that 750 in a moment. All right. I'm also going to erase the question. All right. That way I got more room to work with, but we know we're trying to get the grams of oxygen in the end. Let's do some work for carbon and oxygen and figure out what the formula is. So for carbon, we have 27.29 grams, and oxygen, we have 72.71 grams. Convert each to moles. Carbon's 12.011. Oxygen is 15.999. Get out my Google calculator. All I'm doing is opening up another tab and typing it in. 27.29 divided by 12.011. In this case, I get, with 4 sig figs, I get 2.272. For the oxygen, 72.71 divided by 15.999 with 4 sig figs, 4545. That's what I got. All right. Let's see here. So next, we got to take the lowest value and divide that into each. Well, we know this will be 1, right? Because that's the lowest value. Divide that into itself is 1. This 2.2. Well, I got to write it right. 2.272. That should be 2. Now, you could check your math there, okay? But with 4 sig figs and everything, it should come out to be just about that. You got some leeway in this area, but not a whole lot. Now, I'm actually going to double check myself. 2.272. And I get, with 4 sig figs, 2.000. So 2. So your formula is CO2. And that went right along with our expectation. And that expectation is just part of the analysis. So as you're reading this question, it makes sense to kind of think ahead and go, okay, what could it be? Narrow down the possibilities as you go. So this is the empirical formula. But the question told us that that is also the molecular formula. So far, all we figured out is that it's CO2. So I'm going to erase some of this work. And I know that it is CO2, okay? Now, remember what the question was asking. It was saying, how many grams of just oxygen? All right, well, it turns out, if you look back earlier in the question, we have 750 liters of this gas. Okay, here we go. So 750 liters, that's 2 sig figs, right? Now, the percent composition is in mass, so I have to cancel out liters and go to moles. Being that it's a gas, I can do the 22.4. That works in my favor, saves time. Then I'm going to cancel out moles and go to grams. Now, how many grams are in 1 mole of CO2? Well, let's double check. I think it's around 44 if I remember right. let's see, 15.9. Yep, I got 44.009. All right, I just added it up. Next, this is where you got to realize that we're in CO2 in this step, okay? Now I got to cancel out grams of CO2. We learned how to do this last week. Cancel out grams of CO2, and I want to go to grams of just oxygen. This is where you use the percent composition as a conversion factor. 100 grams of CO2 and 72.71 grams of just oxygen. Now we got to go back and do all the math, and let's get some closure on this question. And while I'm typing this in, you guys got to give me some feedback on that chat so I can see who's with me, who's not, what problems we're having, any questions you might have, anything like that, so I can correct them before we actually move any further, because I don't want to lose anyone, and I want to make sure we're all together and not totally wipe everybody out. Now, 2 sig figs. I got to round my answer to, I got, let's see. Yeah. 11,000 grams of just oxygen. So let's recap what the heck just happened, okay? The question said you have a 750-liter container of a gas. The gas has carbon and oxygen. Percentages were given. You're told that the empirical is also the molecular. And then you want to know how many grams of just oxygen are in this container. So 750 liters of a gas. We figured out what that gas was based on the empirical formula. And then all of a sudden, we did the math. We converted the gas, the amount of gas, using the percentage to get to just oxygen. Hi, Tina. My lovely wife is checking in. She's making sure I'm actually working today. She's out working, and she's making sure I'm doing my share around here. Anyway, I love you, Tina. All right, so we have just concluded that question. And this, I'll be honest with you, this is the question that you would have seen on your test in class. So I really can't guarantee that this will be a question you see again, but something like this is a very reasonable question. Let's see if I got another one. Nope. But you want to do one more? Let's do one more. Okay, this is a good question, but it's going to seem like it's involved. So I'm going to erase all this work, and I'll read the question, start adding up some of the stuff to the whiteboard. Okay, here we go. It says, now keep in mind, I'm a big fan of including extra information in these types of questions, so it makes you think a little harder, right? It's just, problem-solving skills. Some information won't be necessary, so it's part of the exercise. Okay, it says 100 grams of a compound called propanol, whatever, contains only carbon, hydrogen, and oxygen. All right, so propanol, whatever that is, I mean, I know, but I don't want to make you guys feel bad for not knowing, but I'm what you call an expert. So propanol has carbon, oxygen, and hydrogen, right? Did I get it in that right order? Wrong order. Carbon, hydrogen, and oxygen. It says that it is 60% with 3 sig figs, 60% carbon, 13.44% hydrogen. And it does not give a percentage for oxygen at all. We'll figure that out. First question says, what is the empirical formula? Okay, we could figure that. We've done that a couple times now. Then it says, if the molar mass is 120 grams per mole, what is the molecular formula? All right, no big deal. We can do the empirical and then the molecular, right? So let's go back to this thing here. I see chat now. You guys are saying that you guys are with me. Okay, very good. Tina, how you making out? You following with this stuff? All right. Now, here's the issue. We have carbon and hydrogen. That information is provided, but we don't have any info for oxygen. Question says that there's oxygen, but it doesn't give us any info. Earlier, I mentioned that this should add up to 100, so I'm going to make sure that I can figure that out. Let's see. 60 minus 30. I get 26.56. Now with sig figs, it really should be 26.6. All right, so you see what I did, right? I just converted them to grams on the fly, and I got them set up to do our work. All we need is the empirical and molecular. To get molecular, you need empirical anyway. So it's kind of working together. All right, here we go. Let's convert each to moles. This is getting old, isn't it? You kind of see the same thing happening over and over. Well, as a teacher, we do that for good reasons. It's called repetition, and it actually generates like a muscle memory kind of thing. And I'm just filling in all the info that we need to get this. And now let's go back and do the math. At this point, just convert each to moles, and we'll go from there. All right, this comes out to be, with 3 sig figs, 5.00, which makes sense. 60 divided by 12 sounds about like 5. For hydrogen, I apologize for my bouncing screen if it is moving around at all, because I'm typing on the keypad as I do that. Whoa. All right, this with 4 sig figs is 13.33. And then this last one for oxygen, 26.6 divided by 15.999. And I get 1 point with 3 sig figs, 6.6. All right, so this is where we're at, okay? Completely reasonable so far, right? Let's see, where are we? Okay, let's move this thing. There we go. Okay. Next step is I'm going to divide the lowest into each. Turns out the oxygen's value is the lowest. So 1.66 divided by 1.66 is 1. And then I just got to do that for each of these. All right, I think the first one for carbon should be about 3. Yep, with 3 sig figs, I got 3.01. That's 3. And for this next one, 13.33 divided by 1.66. With 4 sig figs, 8.030. All right, now, at this point, I got 3.0, 8.030, and 1. Now, 1's got 3 sig figs. All right, this is 3, 8, and 1. You see how close they are to 3 and 8? You could just call that. So 3 for carbon, H has 8, and oxygen has 1. Okay? Now, with my vast chemical knowledge, I happen to recognize that as the formula for propanol. Now, you wouldn't know that, but you would trust the math and get this answer. I just can confirm it because of experience. No big deal. So that's the formula for propanol. Later on at the end of the moving on. Now, the question says, what is the empirical formula? So we just figured that part out. Then it says, if the molar mass is 120, let's write that down. Molar mass is equal to 120. What's the molecular formula? Okay, so let's move this up here. And I'll use the last part of my whiteboard here to figure that out. So the molar mass is going to be 120 divided by the mass of this thing, right? Well, 3 carbons is about 36, plus another 8, you're looking at 44, plus 16, so it's around 60. Okay? 120 divided by 60 is 2, which means I need 2 of these things. And you distribute, so it's C6H16O2. So you got your empirical and your molecular. And that's really all there is to it. This one was pretty straightforward, being that we didn't have to multiply anything up here in that area. This was just 3, 8, and 1, easy peasy. All right, I'm going to leave it at that, okay? So that's where we're going to wrap it up today. It's been about a half hour. You guys are sticking through this with me. I appreciate it. I'm going to be putting up on Google Classroom an assignment for just determining empirical and molecular formulas, and that will be due on Thursday. So that's something that you should look out for, and go check Google Classroom in just a moment. Actually, give me like a half hour because I got to put it together still. I have questions that I want to use, but I have to actually build the document and go from there. So today was new stuff. Tomorrow is going to be a breather, a Q&A day, and I have a something I want to ask everybody about. So I will do 8 and 9 again tomorrow morning, and we'll figure out what I want to talk about at that point. Thursday, the beginning of each section will be dedicated to questions. So my non-honors class, they have an assignment due as well. At 8 a.m. when I'm with them, I'll take all questions from anybody. So pop in if you want, whatevs. I'll answer questions, and then I'm moving on to new stuff with them. At 9, I'll do the same. Start the class with questions about the assignment or anything that you got, and then we'll move on to new stuff from there. But we are getting towards the end of this unit. There's not much more that we can really do. Yeah. Actually, besides doing a couple extra practice questions, I think that might be it for this unit. We'll see. I got to double check that, but whatever. Okay, so assignment in Google Classroom be due Thursday. Then PowerPoints and all that stuff. Excuse me. All that stuff will be figured out coming up soon. All right, now, this is officially the end of today's lesson, but if you want to hang around, I can explain some upper-level organic chem based on that propanol stuff. It'll just take me a few minutes, and we'll talk about that. So if you have no interest in this, I totally understand. If you don't want to get confused, I totally understand. But if you're curious, this is actually something I'm pretty good at. And when I was in... Whoa, I just had a major malfunction. Hang on. I got stuff falling off my desk. You have no idea what I'm going through to do this for you guys. Tina thinks I'm nuts. Anyway, here we go. So let's go back to the whiteboard. And everything should be working, right? Yep, okay. So propanol, which is related to a thing called propane. Propane is C3H8. Okay? Actually, let's start over. Let's do the first couple. So there's methane, which is natural gas. That's what you use for, Bunsen burners and stuff like that in school. There's ethane, and then there's propane. Okay? Now, the formulas for these are all based on the number of carbons. All right? Meth always has one carbon, or methane, not methamphetamines. That's different altogether. Methane has one carbon, ethane has two, and propane has three. It's just counting 1, 2, 3. Okay? So far, there's still 6 people in here. I find that highly surprising, but hang out all you want because I'm not going to do this much longer. But this is something I was really good at in college, and I find it more interesting than other stuff. Now, each carbon, there's a formula for these, okay? Each carbon needs 4 bonds. Now, that doesn't mean there's 4 hydrogens for each carbon. The structure for these are going to be similar, though. So that's the structure for methane. You got carbon with 4 hydrogens. Now, ethane is going to be down here. I'll do this. It's got 2 carbons. They're going to be linked together. Each carbon needs 4 bonds, so the remaining bonds are going to be hydrogens. That means each carbon has a total of 3 hydrogens. That's why we have C2H6 as your formula for ethane. Propane, similar idea, but there's 3 carbons, 1, 2, and 3. The remaining bonds that make the carbons happy are going to have 4 bonds, or 4, the rest of the bonds for each carbon are made up by hydrogens. And this is how we get C3H8, C3H8, okay? There are other details that, I'm just going to confuse you if I keep going. But anytime you see a compound end in ANE, it's just carbons and hydrogens. Okay, no big deal. If you see something end, you change the name, methanol, ethanol, and a propanol. Now, this is what the question was that we just dealt with, right? It involved propanol. Methanol is now going to have, well, each of these have an OH. Remember the hydroxides that we learned about? A hydroxide makes these an alcohol. So methanol is going to have a carbon with 4 bonds, but one of those bonds has been replaced with a hydroxide. So that's the formula for methanol. Ethanol, 2 carbons. Everything's filled in with hydrogens, except one of them is going to have an OH. All right? So that's the formula for ethanol. This is the alcohol in alcoholic drinks. It's also used as a racing fuel in race cars. It's very combustible. You get a lot of energy out of it, but it's not good for, it's not for, whatever. It's not as, for certain reasons, we don't use that in our cars every day. We use gasoline instead, but ethanol is blended in with gasoline. It's not the main component. Anyway, propanol will have 3 carbons. Now let's talk about propanol, okay? Get rid of all this stuff. Propanol has 3 carbons, and they're linked together. All other bonds for the carbons are going to be made up of hydrogens. There you go. So that's propanol. C3H8O. Remember that formula that we just did? C3H8O. That's going to be the structure for this propanol that we talked about. Now, here's where things get really interesting. You go to the store, like a pharmacy or something. What's up, Nick? Better late than never. You can go back and watch the whole thing. I'm just doing extra stuff now at this point. So I would not recommend basing your knowledge of this assignment you're going to get today on this stuff. This is off-the-wall stuff. I'm just talking. Anyway, watch this. I can take this hydroxide, the OH group, and instead move it from there to there. Okay? So now this is called isopropanol. You might have seen something like that or something similar, like isopropyl alcohol, in the pharmacies. This is the formula for isopropyl alcohol versus just straight propanol. Now, there's a term that you would learn in organic chemistry called isomers, and it's just the same formula but different structure. So that would both of them, isopropanol and propanol, would have the same structure, well, the same formula but different structure. So different structure means it's an isomer, whatever. This can get really nuts, okay? Now, some of you might be thinking, well, Rob, you always put it at the end. You always put the OH there. If I put the OH there, instead I can move it over there. Isn't that the same thing? Think about it 3-dimensionally. If I take this compound and just flip it over, the OH ends up over on this side. It's the same compound. This is a terminal carbon. So if I put it on the end, the terminal or the terminating carbon, it's the same thing. If instead I put the hydroxide here, now you got an isomer. It's isopropyl. But I could also put the OH there, still isopropyl, same structure, because this can be twisted and flipped over where the OH ends up over here. This stuff gets very deep, but I'm going to leave it there just in case you were curious. We can talk about organic chemistry and line structures and stuff like that forever and ever. I just find that way more interesting than some other stuff, and it's I'm actually a little rusty on it, but I was pretty good. Not gonna brag or anything, but I was pretty good at that stuff. Anyway, so that's that. Okay, I'm gonna leave it there. That was probably way too long of a certain explanation on just that junk that's not even on the quiz. I'm going to go make an assignment and put that on Google Classroom now. That will be due Thursday at noon. You have 2 opportunities before then to ask questions about the assignment. We'll have a Q&A tomorrow, 8 and 9, as well as starting any of the videos on Thursday with questions before moving on to new stuff. So that's that. Are we good? All right, we're good. Nick, sorry about being late. You got plenty of time. You can go back and watch the whole thing. No big deal. My voice is actually starting to go. I think my professional radio career is actually not going to ever happen because I'm getting sore throat from just talking to you guys about chemistry. All right, I'm rambling. I will talk to you guys tomorrow, 8 and 9. And there's something I want to ask you guys. I'll say that for the video tomorrow. All right, guys. I'll talk to you again later. See ya.